So, welcome to this week's Origins Colloquium. It's a pleasure to welcome Andrew Mummery to give the talk this week. Andrew received his PhD from University of Oxford, working with Stephen Balbus in 2022, and has received a Leverhulme Perels Research Fellowship, which he's holding also at the University of Oxford. And as we'll hear today, Andrew's developed a very novel way of weighing supermassive black holes and has found some very interesting results. So we look forward to your talk, Andrew.
Okay, thanks everyone for the opportunity to talk today. So just as by way of an overview, I'll introduce tidal disruption events because they are still somewhat of a niche optical transient. So I'll tell you what they are and their power, I guess, as probes of black holes. I'll talk specifically about my work on weighing supermassive black holes through their optical light curves. And then because this is an origins talk, I'll talk about some of the implications of this work and in principle, how we might be able to constrain the origins of supermassive black holes, looking forward to the Rubin LSST era. Okay, so what is a TDE? Well, if you think about a galaxy, we live out here where the stellar density is relatively low. But in the middle of galaxies, there are both supermassive black holes and also an incredibly high density of stars. And, in our own Milky Way, we can zoom right in and follow the orbits of individual stars. So this is the S star cluster, this was Nobel Prize winning work. All I want you to take from this slide is the general sense that the orbits of stars in galactic centers are incredibly densely packed. Okay, and in principle, you could imagine even these stars are going to collide with one another. Of course, this is a two-dimensional projection of three-dimensional orbits, so they're in no sense quite so tightly packed. But this, raises an interesting question of what can happen when you put this many gravitating objects in such a tight space. And so the general picture is, while in, say, an X-ray binary in the galaxy where I have a star, just orbiting a black hole, in the center of a galaxy, this star is also going to feel gravitational sort of n-body interactions from all the other stars in the sort of local neighborhood. These n-body interactions are just forces, so they'll sort of randomly kick the star, they'll change its momentum, which will ultimately change its orbit. And so you can imagine, at least in principle, it's possible to scatter a star arbitrarily close to the central supermassive black hole, just stochastically. Now, this is quite rare, this is quite fine-tuned. So, early work on this subject showed that, in any one galaxy, this is extremely unlikely to happen. Perhaps you get one event for every 10,000 to 100,000 years, or say one event for every 100 supernovae in a given galaxy is a rough comparable rate. Okay, but of course the universe is very big, so there are way more than 100,000 galaxies, so we can easily observe many of these a year, and in fact there are now sort of 100 of these objects which we've detected. And this is only going to grow as we move into LSST. So what happens? You throw a star, almost radially at a supermassive black hole, or you can run a hydro simulation. So what happens is the tidal force, so the differential gravitational force across the object, stretches the star out, spaghettification, if you like, into a long strand of debris. The front end of the debris goes around the black hole, and then the orbit precesses, meaning it will collide with the back end of the stream. Okay. This will then shock the gas. There's a train wreck phase, effectively, of highly nonlinear fluid dynamics. You'll shock heat the gas. This will produce luminous emission, which we can detect. But then eventually, on longer time scales, so sort of months to years, angular momentum conservation effectively guarantees that eventually you will form some sort of accretion flow. Okay. Much of this material is bound to the black hole. You conserve angular momentum, and so you will ultimately form some sort of disk-like structure. That will then evolve on much longer time scales, much longer than you can probe with a sort of hydro simulation, which will continue to produce emission. And so these are the observed systems we're going to see. And one of the yes, you have a question.
Sorry. What is the time scale and the physical scale of that simulation?
So this simulation, you'll note, was done in 2015. So this is a slightly artificial simulation. They've compressed everything. There are now better simulations, but this is the sort of original. It's typically a month time scales for the initial collision to happen between streams. After that, the time it takes to settle into a disk is somewhat of an open question, but observationally, it doesn't seem to take longer than a year. And the actual interception points are typically on the order of tens of Schwarzschild radii for your typical supermassive black hole. So this is a highly relativistic event. Okay, so what's the potential power of these objects? Well, they go off effectively at random around any black hole that is surrounded by a dense enough cluster of stars, which means that in some sense you're going to get an unbiased view of otherwise quiescent black holes. You don't need an actively accreting galaxy to detect these. Eventually, one will just go off, and then this is a sort of unique opportunity to probe that black hole. Yes, another question.
I thought that these TDEs happen preferentially in E plus A galaxies, which is a very particular type of galaxy.
Yeah, so, okay.
Aren't you biasing yourself to certain type of galaxies, to black holes in certain type of galaxies?
So that is true. Of course, we're going to be biased in particular to centrally concentrated galaxies, for example, where there's a more chance of this dynamical effect. The E plus A bias does still exist. It's much less pronounced than it was initially. Initially, they were overrepresented by over an order of magnitude. I think it's now only a factor of a few. So, once we move to hundreds and thousands of sources, you can obviously correct for this to get a more universal approach. But yes, they are still overrepresented in these Green Valley galaxies.
And sorry, another question. So observationally, how do you distinguish this event from, gas accretion or something else?
Spectrally, they're quite different because you have outflowing gas, so you have quite broad emission lines at sort of 10,000 kilometers per second. They're incredibly blue, and they evolve much more rapidly than, say, an AGN. So the spectra will tell them apart from a supernova, and the timescales tell you apart from an AGN, effectively. Yes, yeah, and tidal forces are increase as you make the mass of the black hole smaller. So if you at the same radius in Schwarzschild radii, you have a much larger tidal force for a smaller mass black hole. So these are a natural probe of sort of intermediate mass black holes, if they do exist and if there are clusters of stars around. Okay, so let's imagine one of these has gone off. What do we see? So in the optical UV, which is typically how we find these events, and that's mainly because it's easiest to do an all-sky survey with an optical instrument. They're very bright, sort of supernova up to superluminous supernova luminosities, so 10 to the 43 to 10 to the 45 per second, which means we could, in principle, detect them out to cosmological distances. The sort of typical redshift of a source is 0.1, but we do have them up to sort of 0.3. Decay timescales tens to hundreds of days if you fit an exponential profile to the early light curve. So this is just flux versus time in days in sort of astronomy units. The spectra is very, very blue, and there are well understood or well characterized emission lines which tell us when they are in fact a TDE and not some other nuclear transient. And then at late times, and this will be crucial to this talk, there's a plateau in the light curve, and this is real. Okay, so this flat line you can see from day 300 to 1200 here. So this is actually a source that went off in 2014. So we now have 3,000 days worth of data. This is real to the source. This is an order of magnitude brighter than the galaxy was before the event. Okay, so this is something that's actually physically happening in the system, and the emission is changing from a very rapid decline to basically complete time independence, and that is physical. These are also multi-wavelength transients, so they're also typically X-ray bright. Roughly half of the optically detected TDEs also show some X-ray emission. They can be as bright in the X-ray as they were in the optical, up to sort of 10 to the 44 arc per second. Rapid, typically monotonic decline. There's no plateau in the X-ray. That's unique to optical and UV. And spectrally very, very soft. So nothing like an AGN. There's no big power law component. It's pure thermal emission, like an X-ray binary soft state. So this is really a signature of sort of accretion on horizon and scales in these systems. So accretion disk emission. Okay. So, when people give talks on TDEs, they typically say we're about to enter a data-rich era, but we already have absolutely fantastic data sets on a wide variety of sources. We have really well-sampled long baseline light curves in multiple different wavebands from X-ray through to optical. And if you sort of coarse grain this data like a theorist, there are sort of, in principle, 3 luminosity scales in the problem you might like to understand. There's the peak of the X-ray light curve, the peak of the optical light curve, and how bright is this flat line at late times. And we have a huge amount of data already, which in principle can be very constraining for our models of, say, black hole populations or accretion disks. So on the left, I'm just showing the, histograms of this data, where blue is this late time UV, green is the optical peak, and black is the X-ray. And then on the right, potentially more interesting for this audience, a luminosity function. So this one we've corrected for observational biases. And we have 90 data points for, say, the optical luminosity function. So if we can relate the optical emission to the black hole mass, say, then one in principle can go from a luminosity function to a black hole mass function. Or at least, that's the goal of this type of science. Okay, so that's the sort of goal. What have we been trying to do in Oxford for the sort of last 4 or 5 years now? So the problem we want to understand is if you think back to the simulation I showed earlier, most models for the, while incredibly complicated, most models for the early time dynamics in a TDE ultimately lead you to some sort of disk-like structure at late times. So we ask the sort of spherical cow theoretical physics problem, which is if I have a ring of material, which is my my approximation to once this train wreck phase has worked its way through, and I then let this evolve, okay, it's not going to stay a ring forever. That's, a highly unnatural situation for it to find itself in. How much of this data can I explain just by a time evolving accretion flow? And therefore, by implication, what do I need to add on top of these models to get the whole light curve correct? So that's the problem we posed ourselves. To solve this problem, you need to do some fluid dynamics and general relativity. Effectively, what we do is we write down the Navier-Stokes equation in curved space. There's a very well understood procedure for solving these sorts of problems. Just like normal fluid dynamics, it's a set of conservation equations. So, this ring of material will want ultimately to accrete onto the black hole. It can't do that in any random way. Mass is conserved until I lose material over the black hole. Again, angular momentum is conserved. I don't really want to go into mathematical details in this talk. All I will say is that mass and angular momentum conservation of the fluid effectively tell you how the fluid moves. It's going to evolve. It's going to accrete onto the black hole. Dynamics is constrained by mass and angular momentum conservation. And then as the fluid moves around, as fluid elements move in and out in the gravitational potential field, they'll have to liberate energy to move around. That will be dissipated and ultimately radiated away. So the conservation of energy constraint tells me what I'm ultimately going to see. Okay.
Can I clarify, you're not doing MHD, you're just doing...
No. So this is like a time-dependent alpha modeling type thing, but with full GR.
In equatorial plane or inclined?
Yes, so it's assumed to be in the equatorial plane, which is a bad assumption. Of course, the star won't know anything about the spin axis of the black hole as it comes in. But of course, I can't solve the problem unless I make that simplifying assumption. So, for example, for the optical data, which I'm going to talk about, these are the outer regions of the disk, which are almost Newtonian. And so that systematic effect we don't think will be too important. Okay, so what you ultimately end up is a one-dimensional diffusion type equation. So it's much like the classic Lynden-Bell and Pringle equation, if people are familiar with the Newtonian setup, only upgraded to general relativity. Okay. So I thought I'd just show you, what happens to these rings when you let them go. So on the vertical axis is the temperature of the gas. This is the radiative temperature. So if it was emitting thermally, what you would see. On the x-axis is the disk radius, and then the black holes over to the left. So this is my initial ring in blue. You let it go. What happens is that, there are very steep density gradients in this initial ring, which are unnatural for a diffusive type equation. Material rushes in at early times, quite naturally for an accretion flow. The temperature goes up in the inner regions. And this is just because the fluid is getting deeper and deeper into the gravitational potential well of the black hole. There's more free energy available in the disk shear, so your dissipation goes up. Your temperature then starts to drop with time. This is simply because we're losing material into the black hole all the time, so the density drops, and with the density dropping goes the temperature. Okay, so the inner disk behavior is very simple to understand. A lot of material moves out. Okay, this may be surprising at first glance, but this is just angular momentum conservation. Of course, I can't take a ring and just put it onto the black hole. That wouldn't conserve angular momentum. So some of my gas, some of my fluid has to move out to conserve angular momentum. So if you ask the question, what would I observe? So I then put this disk at 100 megaparsecs, so a typical distance for a TDE. And now I'm plotting the flux on the y-axis versus the frequency on the x-axis. And so the purple band is what an X-ray telescope would see, and a green is what, say, Hubble would see. So on the bottom, I have the temperature, so it's the same simulation. So as I let the disk go, material rushes in towards the event horizon, the temperature goes up in the inner regions, and then over to the right-hand side of my plot, there's an X-ray flare. Okay, my X-ray emission is sensitive to the very hottest parts of the disk. So as material moves in, the temperature goes up, my disk spectrum moves into the X-ray band, and I get an increase in X-ray luminosity. But then I keep losing material into the black hole. My temperature drops, and of course, with my dropping temperature, my disk spectrum moves out of the X-ray band, and my X-ray luminosity goes down.
I think we had a question here. Yeah.
Yes.
Not sure if you can hear me. Can you just repeat what unit the disk radius is in? Oh,
it's in units of gravitational radii, so over GM over c squared. So if this was Schwarzschild, and I can't remember what the spin was, the event horizon would be at 2. And I think for the black hole mass I picked, and for the sun, the tidal radius is at 15, which is where I put my initial ring.
Thanks.
Okay. Yeah, so over in the optical bands, you see something quite different. So over the first cut, this is now the green region of the spectrum. Over the first sort of 100 to 200 days, there's a rise in the flux. But then the spectrum, the flux will just sit there, and it will sit there for 1,000 days in this simulation. But if I kept running this will last for decades in principle. Okay. Now, the physics of this is quite simple. It's just two competing effects which cancel out. So, my disk is always getting colder because I'm always losing material into the black hole. Okay, so my temperature is always dropping. And if I took a thermal spectrum and just cooled it down, I would, of course, reduce the flux at all frequencies. But to conserve angular momentum, my disk is always getting bigger. Okay, so there's more, so the outer edge of my disk grows with time. And of course, if I took a thermal spectrum and I made the area bigger, the flux would go up at all frequencies. So it just so happens that in typical optical UV bands, for typical tidal disruption event parameters, these two effects almost perfectly cancel out. And even though my disk is very dynamic on these sorts of timescales, the optical and UV flux is completely time independent. Okay. And this is a very simplified model, but it really does seem to reproduce the gross features of TDE light curves. So this is just the X-ray light curve I showed at the start. So flux on the y-axis, time on the x-axis. And of course, the real universe TDEs are more complicated than this simple model on short time scales. But over a sort of 1,000 days, we really do seem to reproduce the gross evolutionary properties of these systems. And with the exact same free parameters of the system, we reproduce this flattening in the emission at late times. So we still don't understand what this early flare is in the optical and UV. As a community, there are many models for what this flare might be. It's probably something in this train wreck phase, some shocking of gas. But at late times, after about 1 year, whatever's producing this luminosity fades away, and we transition to just seeing an accretion disk and a flat. Okay. So, this may not look like a particularly interesting figure, but I'm going to argue that this is the most important flat line in TDE science. And the reason is that you can use this flat line to weigh the supermassive black hole at the center of this event. Okay. So I'll explain what I mean by that. So if you think like an observational sort of astronomer here, this is a really convenient property of these systems. As long as you wait at least a year, no matter when you observe the system, be it day 300 or 1200, you're always going to get the same observational answer, okay? Because there's effectively no time dependence in this system, okay? The observations at this late time can be characterized by a single number, which is just the amplitude of this plateau. So how bright is the flat line, okay? So it's very simple to follow up all sources, and it doesn't matter when you do this follow-up, as long as it's at least a year after. You can measure the amplitude of this flat line. And so if you could relate this flat line back to the parameters of the system, you'd have, in principle, a very powerful probe of the black hole. Okay. Now, it turns out that at least with pen and paper, theoretically, you can relate the amplitude of this flat line to the black hole mass in the center of the event. Okay. So there are 5 effects you need to keep track of. Okay, so the first is that, and they're all based on very general principles. They're not particularly fine-tuned. The first is that we're always losing mass into the black hole as we evolve with time, which means that our maximum temperature in the disk drops with time. And if you examine these diffusion equations in a little more detail, you find that it drops as a power law with time. With an index you can describe if you want to go into more detail. But angular momentum conservation tells you that your disk is always getting bigger. Again, these solutions have well-defined behavior. It's, again, a power law of time. So my disk is always growing. There's a fundamental constraint on how much luminosity I can ever get out of my disk, because I've only ever put one solar mass in, or one star in at the start. So that's just a constraint with some accretion efficiency. We know that the innermost regions of the disk are the hottest, so I can relate my luminosity to the mass of the black hole, which sets the radius of the inner disk and the temperature. And we know how big the disk was at the start because we had to overcome the self-gravity of a star by tidal forces. And this imprints a radial scale on the problem. Okay. Now, it turns out that these 5 constraints are closed. And so you can relate the amplitude of the plateau, depending on where precisely you are in the spectrum, to the parameters of the system. Okay. Now, it depends whether you're seeing emission from the very outer edge of the disk or from somewhere in the middle. But then the really nice result is that both luminosities, no matter where you are in the spectrum, scale with black hole mass to the 2/3 power. Okay. So we should have one unbroken scaling relationship between an observable and the black hole mass. And of course, there will be scatter in this relationship. Yes, go ahead.
I'm just wondering, the origin of this emission, is it reprocessed emission from the middle and outer edge of the disk, or is it the emission which comes from the very inner parts of the disk?
So it's thermal emission, so it's direct emission from the disk, but it is the outer regions typically. Typically, the inner regions are hotter than optical and UV bands. So you are seeing the outer sort of 100 gravitational radii scale in the disk.
And is it reasonable to neglect the fact that the inner emissions from the inner part of the disk are expected to be, reabsorbed and in the outer parts of the disk and re-emitted? I mean, this is what happens in protostellar disks. We know this for sure. Why doesn't it happen in this ones?
So they're very compact. So the disks are very small as well, at least initially, and that's because you've had to rip apart a star to form it initially. So that imprints a small scale. So you have to really bend photons to hit this outer disk effectively. So you don't have a big area to illuminate a large radii.
So this is just thermal emission from the photosphere of the disk. Yes, we get a regime where you're optically thick in the outer disk.
Yeah. So you can check. I mean, these equations solve for the densities, so you know the scattering optical depth, and you're comfortably optically thick for typical parameters.
Right.
So there will be scatter in this relationship, and that scatter just comes from the different stars that you throw in. That will put more or less mass in the disk. There are more subtle effects about how big the disk was initially. And of course, you're observing a two-dimensional structure. So there's scatter from just the random inclination angle of the system in your line of sight. Okay. But you can get a handle of this scatter by just numerical simulation. So that's what we do. So we take a million TDE systems. What I'm going to do is uniformly sample black hole masses from 10 to the 4 to 10 to the 9. Okay. And then for each mass bin, I'll take a star from the IMF, throw it at the black hole. If it can be ripped apart, I lay material down in a ring set by the tidal radius, solve my equations, evolve it forward in time to 1,000 days, when I know all of this early time stuff that we don't fully understand as a community will have gone away, and then observe it at a random inclination, with a cos-I uniformly distributed. And then I can just scatter plot this and see what the scaling relationship is. So on the y-axis, I have nu, which is the observable in sort of the U band. And on the x-axis, I have black hole mass. And then each pixel is colored by the log of the number of TDEs. So the first thing you can see is that there is a scaling relationship. Of course, the 0 to 100 percentile scatter is very large. And that's because there are wide range of stellar masses, etc. But for 1 sigma, it's quite tight. So the yellow is thousands of TDEs in a pixel, whereas the green to purple is tens. Okay. So if you observe, if you take this model seriously and you observe a plateau luminosity of a given value, you get typically about 0.5 dec in scatter in your inferred black hole mass from this scaling relationship. Okay. A systematic theoretical scatter. Okay. So of course you want to test this with observation. So we have so at the time when we did this first, we had 84 TDEs. You have light curves that look like this. So what you want to do is you want to model out this early time decay and then measure the amplitude of the flat line, which I'll just call a constant P. Okay, so we tried a couple of different decay laws, power laws, exponential. It didn't really make any difference. Of those 84, we were able to extract with robust statistical significance the plateau in 50 of 84. Okay. And then what you do is you go away, you get an independent estimate of the black hole mass from a scaling relationship effectively, so M sigma or black hole mass galaxy mass, and then you can overplot the theoretical population. And so this is what this plot is. So now the gray points are the simulation I showed on a few previous slides. You can no longer tell the relative density of points because they all overlap. But the colored points are real, optical TDEs discovered by ZTF. So the y-axis is the G band that ZTF measures. And then if the point is plotted in orange, we had a galaxy mass for that galaxy, and we used Green et al.'s scaling relationship between galaxy mass and black hole mass. If it's plotted in green, then we had a sigma measurement, so we used M sigma. Okay. And so, this really does seem to track the theoretical prediction. And this is really exciting. Because it's really exciting because, of course, what you don't want to do is use galactic scaling relationships to probe disk physics. What you want to do is use disk physics to probe galactic scaling relationships. So you turn this whole exercise around, you use every observed plateau luminosity, you project across this distribution, which will give you a mass posterior, and then you can add this to galactic scaling relationships. So this is now black hole mass versus galaxy mass. In gray, I show Green et al., which is a review article, a summary of other measurements. And then in blue are the TDEs we can add to this plot. So you see what's really nice about this is that we are consistent with the sort of slope and intercept of the scaling relationship at higher masses. But TDEs are probing a fundamentally lower mass regime. Okay, we're typically sensitive to below 10 to the 7, down to 10 to the 5. And I guess in particular for this audience, there is maybe one TDE which wants to be below 10 to the 5, but it is also consistent within 1 sigma with being above 10 to the 5. Okay. And you can do the same. You can do the same with M sigma. So again, gray is other techniques, and then blue are the TDEs that we can add. Okay. So I seem to be running on a bit. Is it okay if I keep going? Because there were some questions.
Yeah, you've had lots of questions already, so please go on. And
Okay. Okay, so you want to take this one step further, okay? Rather than just, or in addition to using this approach to measure individual black hole masses, you'd like to say something about populations of black holes, effectively. That would be the key physics goal here. And so the observation of this plot is that, of course, real TDE systems are not uniformly distributed in mass. Okay, now my gray points are uniformly distributed in mass. Now, clearly the colored points are not. So what we can use, schematically, is we can use the observed plateau luminosity distribution to try and infer the black hole mass distribution. Okay. Now, what I'm going to assume is I'm going to parameterize a black hole mass distribution. So I'm going to take a sort of classic Schechter function. So I have an exponential suppression at high black hole masses, which is just a result of basically running out of high mass galaxies. Okay, this exponential suppression really doesn't enter the analysis much because you typically run out of volume to TDEs way before you hit that scale. So I won't fit those parameters. And then I have a power law, which I then allow to be a broken power law. So this will allow, for example, for a break in the mass function, which some models for supermassive black hole formation predict. Okay, so this is, I'm just going to parameterize this model and then try and fit it to the data. So schematically, I have three free parameters, two indices and a break scale. For any one set of these parameters, what I can do is sample from this distribution, do exactly the same procedure as I did for my uniform mass distribution, and get a plateau luminosity distribution. I can then compare that plateau luminosity distribution to the observed distribution in a sensible way. And then I can iterate in a Monte Carlo technique and try and fit the parameters of my mass distribution to the observed plateau luminosity distribution. Okay. So does that, okay, so hopefully that makes sense. So we can do this. So this is a paper that actually came out on the archive this morning, which was good timing for this particular talk. So I want you to focus on the green curves for the moment. So that is the observed mass distribution. So that is, d number of black holes by d log mass of black holes. And this is specifically the number of black holes in our observed TDE population. Okay. So what we can do, of course, this will not be the intrinsic distribution of black holes for various Malmquist biases and other effects. We are able to constrain the slope of this black hole mass distribution above 1 million solar masses. And in the observed distribution, we do want, at quite high significance, a turnover in the mass function at roughly 1 million solar masses. Okay. Unfortunately, with AT sources, we start to run out of volume, observing volume at this low mass end. And so we actually have very broad uncertainties about how this turnover behaves. Okay, below 1 million. The data does want a turnover, but this, at the moment, we're not sure if that is an intrinsic turnover or just a Malmquist effect. Okay. But again, I stress that we don't need any black hole to be below 100,000 solar masses in our population at the moment. So, of course, the question is, okay, you've constrained a mass function. Does it actually work? So yes, it really does work. So this is the PDF of the plateau luminosities. So the histogram is the actual data. And then the purple is if I take this mass function and then fold it for the full framework of the disk model. So it's perhaps rather than a PDF, it's easier to see as a CDF. So this is statistically indistinguishable from the data. So it really does look like all we need to do to reproduce the observed distribution is have a parameterized mass function and disk theory. And we also get the actual rate correct, well, once correcting for Malmquist ones. So what I think is quite nice is to look at this as a sort of 2D plane. So on the y-axis is, again, the plateau luminosity, and on the x-axis is the black hole mass. And then now, rather than a uniform distribution of black hole masses, I use this median of our fitted posterior in gray, and you see that this really does seem to work in a two-dimensional plane as well as just a one-dimensional CDF. Okay. So the final point I want to talk about is a critique of this work would be to say, well done, you've discovered statistics, you've done maximum likelihood inference, and you have managed to fit to the data. That doesn't necessarily tell us that the parameters of your model are physical. So to test whether we can get whether this really does seem to be probing the physics of the events, we pose the question basically, can you get the X-rays for free? So if you remember back earlier in the talk, I said that this model can also reproduce the X-ray light curves of individual TDEs. Now, of course, if I have a disk model, which I think describes the UV and the X-rays, and I've fit a black hole mass function to it, then I should reproduce the observed distribution of X-ray luminosities with no further free parameters, if what I fit is physical. Okay. But this is something you can test. You just do exactly the same procedure. You sample 1 million TDEs, you use the mass function we've tried to measure, and then you evolve the system. And then rather than wait 1,000 days and measure the UV luminosity, you just let the disk evolve. You measure how bright does it ever get in the X-rays, and then you save that value, and then you can compare to the data. And we really do get this X-ray luminosity distribution for free. So this really does just drop out with no further free parameters. And again, this is the PDF in luminosity space, and the CDF here. And so again, by a 2-sample KS test, this is formally consistent with the data. And you can see this.
Andrew, you were saying the X-rays do not show a plateau. So is that the X-ray emission at some defined time?
That's effectively, I'm going to have to just go back a few slides to answer that question. So it's effectively because the X-rays are coming from the Wien tail of the disk. So you get the cooling effect, but you don't get the compensating area effect. Okay. So the X-rays will just keep going down because the X-rays are coming from the inner disk. So the size is fixed with time effectively.
Mm-hmm.
So the X-rays should be monotonic in these models. Okay, which is why we go to the peak of the light curve rather than late time behavior.
Right. So even though in this train wreck phase, which dominates the peak of the optical, it's happening at that time. You're saying that the X-rays at that time.
Yes. So this has this has strong implications for TDE physics. So what my interpretation of what this is that the peak of the typical evolution of the peak X-ray luminosity in time. So how long it takes to substantially move away from the peak is longer than the typical train wreck phase, effectively.
Okay.
So that's the statement I think is the most likely to explain why this works without including a train wreck. Yeah. And I just want to highlight that there is actual structure to this result. It's not like everything just scales with the Eddington. On a 2-dimensional luminosity mass plane, the X-ray luminosity has a very different structure to the UV plateau luminosity. Okay. Yeah, and so that's everything I have time for. I want to just say that LSST does expect to discover 80,000 TDEs in the next decade. If you believe their estimates of rates. And so I really do think that we will be able to very much narrow down the uncertainties on these mass turnovers and the black hole mass function, hopefully in the next few years. So yeah, thank you very much.
Great, thank you.
Cheers.
Plenty of time for questions. So we've got 3 rooms here. Joe in Sweden and Devesh in Virginia, if you can moderate there. Questions for Andrew? Yuri?
I was just trying to do this math in my head, and if the angular momentum of the disk is conserved, that means that the product of the disk mass and the square root of its mean radius has to be conserved, right? So this means that the radius of the disk has to scale as the mass of the disk to the minus second power, right?
Yeah. Yes, it does.
Doesn't it mean that you are extremely sensitive about what you assume about accretion? Because accretion, of course, is mediated by this fully
I'm sorry, you're breaking up. I can't hear the second half of this question.
Can you hear me now?
Yes, I can.
Doesn't that mean that you are extremely
Oh,
sensitive
sorry,
to what
you've gone again. I don't know if it's just.
Let's try again now. Can you hear us, Andrew?
Yes.
Can you hear, Andrew?
Yeah.
Does this not mean that you are very sensitive about what you assume about accretion parameters, like alpha, for example?
Yeah. So I didn't mention alpha in the summary of the slide, but I also marginalize over a factor of 100 in alpha effectively. I go from, I have to parameterize a viscous timescale in the system, which effectively you can think of as what is alpha, if that's how you like to pose the question. So I also uniformly sample from 10 to the minus 2 to 1 in alpha, which what that does is broaden the scatter effectively here. Yes, it's I don't normally mention this on the slide because it's goes down a bit of a rabbit hole, but yes, that is it does. There is a functional dependence on alpha as well.
Okay, thank you.
Well, I had a related question. I mean, if there are large-scale magnetic fields which are transferring angular momentum, and there's a disk wind which is sucking up some of the energy, and there's mass loss, do you have a sense of which direction it would go in terms of measuring would your mass be overestimated or underestimated?
So I don't. You have effectively 1 star's worth of magnetic flux to start with. So I don't think we typically have to worry about, say, these mad accretion states which people invoke for other systems. I think the fact that the spectrum is so thermal in the X-rays and it's not the power laws tell us that we don't have these coronas that also dominate in other systems. So, I mean, it is an interesting question about why does this work so well? This is a very vanilla model. If you were to carry significant mass out, if the disk masses were systematically lower than we're assuming, to get the same plateau luminosity, you need a higher mass. So we would, in that case, be biased to lower masses that we infer. If you're blowing mass out and therefore reducing the mass in the disk.
So that effect would mean that currently your masses are underestimated.
Yes.
Okay. Any other questions for Andrew? Ilsan, please.
Yeah, thank you, Andrew. I have a very naive question. I mean, this is fascinating idea, a lot of huge implications in the LSST. But if that sort of the isolated system sort of circle around the black holes give you sort of the plateau, which is sort of the stationary over time, what's the difference? Let's say we have even if we don't have a tidal, the TDE, we do have a accretion disk around the black hole, right? If it's the same material still falling in, have some sort of the structure, not exactly the same system you investigate, and then do we also have some sort of the similar implications? Okay, that levels of luminosity stable over time without TDE will have some implication on the measuring of the black hole mass. So am I missing something, or is it? I'm sorry, is this very naive? But
well, I mean, I get. Are you asking effectively? Could you do this for AGN as well?
Yeah, something. Yeah, other than TDE.
So So AGN seem to be more complicated in the optical and UV than TDEs. I mean, of course, people have tried this, and as a general rule, disk theory seems to work less well for AGN, or naive disk theory seems to work less well for AGN than TDEs. Why that may be is relatively hard to understand. It's possible that the environment is a little bit different in TDs. It's cleaner, there was nothing there before. So if this is reprocessing, if in AGN reprocessing is getting in the way, that might explain it. In principle as well, maybe they've not had long enough time, these TD systems, to form a corona and go into different states, which again might make things more complicated. But people do try and use disk theory to measure black hole properties in AGN. But I think for some reason that we don't fully understand, there seems to work less well there.
Right. Thank you.
Another question here.
Yeah, thank you for the fascinating talk. I was thinking, how sensitive are the results to the mass of the accreted star?
So we can yeah. So I mean, yes, there's a scaling relationship you can write down. It depends on the mass and radius. If you assume a sort of standard textbook mass radius relation, the luminosity typically scales with stellar mass to about 2/5 power, so 0.4 to 0.5. So it's not as strong as the black hole mass, and of course stars will vary across the whole population by a smaller fraction than black holes will vary in principle. But that does change the plateau luminosity, yes.
I was going in the direction that if the data fits so well with a one solar mass star, might mean that the typical stellar mass in that area is one solar mass. So I don't know if that's a way to constrain any like top heavy IMF or something like that.
Yeah, so okay, this is great. Yeah, so this is a fantastic question. The results I presented at the end about constraining three parameters in the black hole mass function, we were originally much more ambitious and also tried to constrain the IMF in galactic centers and the spin distribution. And what we just found with ZTF and AT sources is that we can't distinguish between different IMFs at all. There's not enough. Because of the weaker dependence, we can't answer that question. So we took the simplest result, which was Krupa IMF. But with LSST, I really do think a joint analysis would be able to work, and that is something we are looking at going forward.
Right. Can I ask that eventually the plateau must decay away, right? So is there evidence for that happening?
We have no evidence for them going away, and the record is 11 years and counting. They do I've said they're a perfect flat line. That's not strictly true. Some of them are slightly tilted, but in terms of disappearing, currently 11 years, and that's just because the first one was discovered in 2014. So,
but your models predict when they should go away, or don't they?
Yeah, I mean, 100 years is comfortable. But I would expect if they are like big X-ray binaries, say, typically you have some sort of state transition that will kick in before that. So in principle, you can ask disky questions as well. But as of yet, we have no evidence for them going away.
Does that constrain alpha at the moment? I mean, if you had high alpha, they go away quicker, I guess.
Yes, that is in principle a question you could ask. Yeah.
Great. Any other questions for Andrew? I did want to come back to your result on the mass function. I was asking by email yesterday, but you sent the figure. So right now, what is your error? You've got this big blue shaded region that's grown from the green shaded region was smaller. Now the blue is bigger.
So the green shaded region is so where does the uncertainty come from? So it's just it's effectively trying to fit for beta in this equation, which is what is the slope beyond the turnover. And effectively MCMC techniques have very little constraining power. So a whole range of power law indices are consistent with the data. And so then it's just so this range is just uncertainty in that parameter. And so it's, basically I produce this plot by sampling from my posteriors and making a mass function for each one and then looking at the variance.
Right. Could you try, or have you tried fitting a function which has a cutoff at low mass?
I did not, because I thought this was relatively agnostic and could mimic a cutoff. But if someone has a mass function they believe in and wants to test whether it can reproduce TDE observables, that is a question that's very simple to ask now with this pipeline.
I think it's just add you've got to effectively, you've got to check, you've got this exponential suppression at high mass, but maybe we just try something with that at low mass.
Yep. Yeah. Yes. These are. It's an industry now. We have these codes, and so if you can parameterize it, we could run the analysis.
Can you show the mass function again now? By when do we? It's very tantalizing. This what's shown here. Do we have to wait for LSST 80,000 events, or do we just need 160 events, or what?
That's a good question. I think so. Okay, a lot of the 85,000 you find won't be particularly useful because they'll be the bright ones and they'll be at the high mass end, which isn't constraining. I think effectively, if you just really don't find these low luminosity events after a few years of LSST, then this will happen. I can't answer well a number or even an order of magnitude about what we might need.
All right, Devesh has a question, and then we'll probably wrap up.
Sorry, just a quick question. Wait, why am I going?
Sorry, yeah, sorry. The question was really for these the stars that you are undergoing these tidal disruption events. Do we take into account the evolutionary stage they're in, or the chemical composition itself of the stars, or is that a bit further into?
I don't. People do think about this. So people do work on metallicity impacts on the initial disruption, those sorts of questions. I'm using effectively zero age main sequence, which which is not strictly correct, of course. But as I said, we weren't able to constrain the stellar mass distribution from the data, so I don't think at the moment those effects are impacting our results. But these are the sort of questions when you move to very large samples, it does have an effect. Effectively, the composition of the star affects the puffiness of the star and how hard it is to disrupt effectively.
Great. Any last questions for Andrew before we stop the main session? If not, let's thank Andrew again for a great talk.
Thank you very much.